Welcome to Next Gen Manufacturing. In a world that's buzzing with AI-driven factories and amazing new materials, it's pretty easy to get lost in the big picture. But what if I told you that the future of all that stuff, it really comes down to something you could probably cover with your thumb? Today, we are drilling down, pun intended, into one of the most basic yet surprisingly difficult parts of modern engineering, the perfect hole. So just picture this for a second. You're machining a really critical component, something that has to be absolutely flawless, down to the micron. What do you think is the most common everyday threat that can just throw the whole process off the rails? Is it some complex software bug, a giant machine failure? Well, the answer? It's probably not what you're thinking.
Yep, it's not the robot, it's not the software. It's a single, tiny, misaligned hole. That's right, one of the most frequent and, let's be honest, frustrating issues that machinists face can bring a multi-million-dollar production line to a complete stop. It is the tiny error that causes massive, massive problems.
And believe me, those problems are very real. This isn't just, a small inconvenience. We're talking about a direct and pretty big hit to the bottom line. So let's take a look at the actual cost of getting this one little detail wrong.
Think about modern manufacturing like it's a high-stakes puzzle. Every single piece has to fit together with absolute perfection. If a hole is off by even the width of a human hair, that puzzle piece is basically useless. You can't fix it. The whole part, which represents hours of machine time and a lot of expensive material, it goes straight into the scrap bin. We're talking billions of dollars a year globally in waste from this kind of thing. That is a direct hit to your efficiency and your profit.
Okay, so let's get into it. To fix the problem, you first have to understand the problem, right? A misaligned hole isn't just one thing. It usually shows up in two different ways. And knowing the difference between them is really the first step to stopping them from ever happening.
So, over here on the left, you've got angular misalignment. Imagine you're trying to push a perfectly straight rod through two holes, but they're tilted, even slightly. It's just not going to work. Their center lines aren't parallel. Then on the right, you have offset misalignment. Now here the holes are parallel, but they just don't line up. The center lines are shifted, so again, nothing's going through both of them correctly. Two different issues, one very expensive outcome.
So, how do we fight back? How do we prevent these errors? Well, our first tip is all about setting yourself up for success from the very first moment the tool touches the material. It's a really simple, but kind of brilliant preventative step.
It's called a spotting drill. What's so cool about this thing is its one and only job. Before your main drill even thinks about getting close, this tool comes in and creates a small, super precise little mark. And that little divot, it acts as a perfect guide, making sure the main drill bit doesn't walk or wander off center when it first makes contact. It's like the pilot for the main mission.
Now, I know what you're probably thinking. Wait, doesn't that just add an extra step? And yeah, you're right, it does. The cost is one extra, really quick tool change in your process. But the payoff? It's pretty much a guarantee of a perfectly placed hole. It is a tiny, tiny investment in time for a huge return in accuracy.
And there's this great quote that just nails it perfectly. The time spent in a tool change is far less than the time required to redo a project due to a misaligned hole. Just let that sink in for a second. A few seconds of prevention can save you hours, maybe even days of having to remake something. It's all about working smarter, because throwing a part away is the biggest waste of time there is.
All right, let's move on to tip number 2, because getting the surface ready is only half the battle. Now we've got to look at the tool itself, and more specifically, the kind of hidden anatomy of the drill bit.
Meet the web. This is the central core, the backbone of the drill bit. And as you can probably guess, a thicker, bigger web makes the drill stronger and stiffer. And that sounds awesome, right? More strength, more stability. What could possibly go wrong? Well, here's the twist. And this is what I love about engineering. It's a complete paradox. If a thicker web makes the drill stronger, like a heavyweight champion, why does it sometimes cause it to trip right at the start? How can adding all that strength actually make you less accurate?
Well, the reason is at the very tip of that super thick web, it's less of a sharp point and more of a blunt chisel. So when it first touches the material, it has a much higher chance of just skating or walking across the surface before it can actually start to cut. And just like that, despite all its strength, the drill starts your hole in the wrong spot. You're right back to where you started, fighting misalignment.
But the solution is this really elegant piece of engineering. It's called web thinning.
You might also hear these called split-point drills. This design gives you the absolute best of both worlds. You get a thick, rigid web along the body for all that strength, but then a thinned, super sharp point right at the tip for pinpoint accuracy.
And the benefits here are just crystal clear. First off, this design is way less likely to walk off center. Plus, it needs less force to push into the material, and it has less resistance as it cuts. All of that adds up to a cleaner, more accurate, and just a more efficient drilling process all around. Okay, this brings us to our third and final tip for today. And this one is just fundamental to pretty much any machining process. You gotta choose the right tool for the job.
To put it simply, don't use a one-size-fits-all approach. It just doesn't work. Different materials act in totally different ways. Aluminum is soft and can gum up your tool. Stainless steel is tough, and it has this nasty habit of getting even harder while you're cutting it. And something like titanium, well, that's in a whole other league. Using a drill that was made for your specific material isn't just a good idea, it is a total game changer.
And here's why they work so well. First, the geometry, the actual shape of the cutting edges, is perfectly optimized to handle whatever that material throws at it, whether that's clearing out chips or handling a lot of heat. And second, they have these specialized coatings that cut down on friction and wear, which is absolutely critical for staying accurate for the entire life of that tool.
So we've covered 3 really practical, actionable tips, right? Use a spotting drill, pick a split-point drill, and match your tool to your material. But let's just zoom out for a second. Why does getting this one little detail right matter so much in the grand scheme of things?
Because really, this isn't just about making one good part. This level of fundamental precision, it's the bedrock that all of next-generation manufacturing is built on. I'm talking about everything from jet engines to medical implants. These incredible, huge innovations are only possible because of millions and millions of perfectly executed tiny details. The perfect hole isn't just a hole, it's literally a building block of our future.
And that kind of leaves us with one last thing to think about. These techniques, they give us the power to create one perfect hole. But what's the real potential when millions of those perfect holes, inside millions of perfect parts, all come together seamlessly? What new technologies, what new frontiers does that level of precision unlock for every single one of us? Thanks for joining me today.